final lesson in chapter 16, and I know we're going to be sad. This is the final lesson of the year. So in today's lesson, we're going to turn things around from what we've been doing electrochemically. And instead of having a voltaic cell that uses a spontaneous reaction to produce electricity and gives us a positive net voltage, we're going to look at electrolytic cells. And normally this would be done as a demo in class, but I've got some videos that I have for you to watch. The videos are listed under each demo number, and you should watch the video before completing the demo. That way you'll understand what's going on. An electrolytic cell is a non-spontaneous reaction. So these are electrochemical reactions that are non-spontaneous, but that are forced to occur by putting in electricity from a battery or a power source. And because they're non-spontaneous, we're going to see that if we put together the reduction and the oxidation reactions correctly, we will get a negative voltage for that cell. So in the first demo, we're going to have our Hoffman apparatus. Now, if you look at the diagram at the right, you'll recognize this as the equipment that I used a while ago to split water into hydrogen and oxygen. But now we're going to look at it from a slightly different point of view. We're going to have some sodium sulfate in there. The sodium sulfate is there as merely a neutral electrolyte, so it helps conduct electricity. But as you'll see below, neither the sodium nor the sulfate will react. And the indicator bromothymol blue. And as you can see, it starts off as green in the neutral solution. So go ahead and watch the video. And I have you starting a little ways into that video. If you want to go back and watch the beginning of the video, you can. But otherwise, from where I've got it started, you're fine to go. All right, so hopefully you went and watched the video. If not, go and watch the video at some point. Make sure you understand what's going on. So to understand what's going on in this electrolytic cell and why the colors are the way they are, and I'm sure she explained it as well, we have to figure out what's in solution. And this is key to any electrolytic cell. We have to figure out what's in solution so we know what's present to be oxidized, what's present to be reduced. So there's actually three things in the solution. We've got the sodium ions, so sodium plus ions. We've got the sulfate ions. And what's not as obvious, but you have to remember this is an aqueous solution. And we've got water present, and that water can undergo electrochemical reactions. In this table below, I have listed the possible electrochemical reactions. I've pulled these off of chart H. I'm not going to have you go searching for them because one of the tricks is we have to recognize the reduction and the oxidation. So remember, the oxidation is taking place in the reverse direction. So water can be oxidized, and when you oxidize it, you're going to make oxygen gas and some hydrogen ion. And water can also be reduced. And so reducing water will make hydroxide and hydrogen gas. The other things that are possible to happen is that the sulfate could be oxidized, and this gets oxidized to a peroxysulfate, I think that's called. Don't worry about what it is. That actually is an oxidation there. And we're losing 2 electrons. And the sodium could be reduced to sodium metal. Now, there's a couple of things going on here. Notice that I've got the reduction potentials turned around now as an oxidation potential. In all cases, we are going to be able to have the reaction that has the least positive, the least negative, the most positive one is going to be the reaction that works. So the most positive oxidation and the most positive reduction are the ones that are going to be the ones that take place because they're the ones that are going to be more spontaneous. Even though we're pushing them in the backwards direction, they're going to be more spontaneous. So the water and the water being oxidized and the water being reduced are going to be the reactions that take place. And we've got some keys, some clues there that's going on. So when we look at the colors in the left and right hand tubes, we see that we've got yellow on the left, and I'm not going to use yellow because it doesn't show up very well. So let me put yellow on the left, and let's put blue on the right. Now, label the diagram with the color, and we see that yellow means we have an acidic solution, blue means we have a basic solution. So that means we must have OH minus being produced in the right side, and we must have H plus being produced on the left side. And if you look at the product, you can see which gas is being produced at which, in addition to the fact that the oxygen should be produced at half the amount of hydrogen. We can see now that oxygen and hydrogen are going to be produced in the left cell, and the left cell, we already got anode and cathode labeled, sorry about that. The anode here, and on the right cell, we have the cathode, and we're producing hydrogen gas. And notice the signs are backwards now. The signs are backwards. This is the negative cell. So now the reduction at the cathode is the negative cell because that's where electrons are getting pumped into. Now we're making it negative, not because it's attracting electrons. We're making it negative because that's what it's attached to on the battery or the power supply. This funky little symbol here, if you haven't seen that before, that's a symbol for a battery or a power supply. And you'll see more about that in physics. On the left side then, that makes this the positive electrode because the electrons are being repelled by that electrode. They're coming out. And electrons are always going to come out of the anode, right? And they're being attracted to the positive end on the battery. So this is some clues about what's going on. Now let's put together our reaction. The oxidation, as we said, we've got our 2H2O, and that's being oxidized to oxygen. What's being oxidized is the O. The oxygen is going from a -2 to a 0. Oxygen gas plus 4H plus. There's no oxidation taking place there. The H is going from an from 1 plus to a 1 plus, and we have 4 electrons, and the E naught for that oxidation is -1.23 volts. In the second reaction, the reduction reaction, we've got 2H2O plus 2 electrons forming 2 hydroxide and H2. Now what's being reduced is the H plus. It's going from a +1 to a 0. The O and the H in hydroxide aren't changing, and that has a voltage of -0.83 volts. Notice we need to double the second reaction, so rather than just multiply by 2, I'm going to change my coefficients. We need a 4, a 4, a 4, and 2 H2 gases. And so now the electrons cancel out, and we can add everything together. And when we do, we get 6 H2O on the left. We get 2 H2 plus O2 plus 4H plus 4 OH minus. Now the thing is, H plus and OH minus don't always stick around, because when you put an H plus and OH minus, they form 4H2O. So I'm going to erase that, put in 4H2O, but now the 4H2O cancels with 6H2O on the left. So if we cancel 4, we end up with 2H2O giving us 2H2 plus O2. And this is the decomposition reaction for water. And the net reaction, if you add those together, is a negative 2.06 volts. And that means that the voltage supply, you must supply greater than or equal to 2.06 volts to get this reaction to go on. And the fact that it's negative is what tells you that you needed to put electricity in to get this reaction going. Okay, so now that we've had our first look at an electrolytic cell, electrolytic reaction, let's look and see what happens when we put some things into the solution that might react other than water. Oh, by the way, here's another way of remembering. The sodium is never going to work because sodium, if you actually had sodium metal in water, the sodium metal plus water is a single replacement reaction that makes sodium hydroxide and H2 gas. And so there's the hydroxide and the H2 gas that would be formed. So what would really happen is that the sodium metal would end up reducing the water, doing the reduction for the water anyway, and going back to its original state. So this is another way to remember that sodium, and in fact, all of the alkali metals and alkaline earth metals will not stick around in water. They all have way too negative a reduction potential, and water is always going to be easier to do than those guys. Next demo, we're going to electrolyze a solution of potassium iodide. And so we're going to take 2 graphite electrodes and we're going to put them into a solution that has some potassium iodide along with some phenolphthalein, because we want another way to look at the production of hydroxide at the cathode. Sorry. So go and look at the video, watch the video, and you'll see how this works. And now let's come back and take a look. Now we have, again, 3 things that can be that can do oxidation reduction reactions. We have potassium can be reduced. We have iodide can be oxidized, and water can be both oxidized and reduced. And look at the oxidation half reactions. You can see now that the iodide being oxidized to iodine is more positive. So that's the reaction that's going to work. Meanwhile, like I said about, this shouldn't be potassium. This should be sodium. Sorry, potassium should have been changed to sodium here. And so I'll make sure that gets changed before I upload the empty notes for you guys. So, but the water is still going to be the one. Do I have the right E naught for that? Nope, I've got the sodium E naught. Sodium, the water is still going to be the thing that gets reduced. So what was observed at the anode and the cathode? What you should have seen in the video is that at the anode, we have a brown substance. Let me see if I can mimic brown on here. Brown substance. And that brown substance was really the result of the iodine reacting with some iodide that's left over to make the triiodide anion. And that triiodide anion is what's brown. So at the anode, we see that the iodide is being oxidized to iodide. Meanwhile, at the cathode, what's going on at the cathode? We see bubbles. And we see that the phenolphthalein turns pink. I'm going to find a pink someday. And so what does that indicate? That indicates the presence of hydroxide, and the bubbles are the H2 gas that's being produced at the cathode. So let's write the overall reaction then down below. And let's see, we've got the negative, we've got the anode listed with a negative sign, cathode as the positive sign. And let's fill in our oxidation and reduction. So the oxidation, we said, was the 2-iodide being oxidized to iodine and 2 electrons, and that was a negative 0.54 volts. The reduction was our 2 waters plus 2 electrons, giving us 2 hydroxides and H2 gas, and that took place at negative 0.83 volts, crossing off the 2 electrons, and we've got no hydrogen ion here to react to combine with the hydroxide, so that's not going to happen. So we've got our 2 iodide plus our 2 waters coming together to make iodine plus 2 hydroxides and H2. And the E naught, the overall voltage for that, is negative 1.37 volts. And again, that tells us that we needed to apply at least 1.37 volts. And I think our little 9-volt battery is more than enough to get that done. All right, halfway through, let's take a look on the next page. So on the next page, I'm going to make things a little simpler for you. So on the first, in those first 2 reactions, we have water around that could be oxidized or reduced. Now we're going to look at the oxidation or the electrolysis of a molten salt, in this case, lead 2 bromide. And lead 2 bromide is picked because it has a fairly low melting point, so it's easy to get to the molten state. Again, when you look at the video, you'll see how this works, and recall that we do need to have the salt molten in order to get it to conduct electricity, and they'll talk a little bit about that. So we've got 2 graphite electrodes in the video. They're attached to a power source. It's not a battery this time, it's just some sort of a power supply that can provide a DC, direct current power supply, and they're placed into the molten lead bromide. So watch the video and now come back. And the species that are present in the melt, this is easy now. There's only 2 things present. We've got Pb2 plus that can be reduced, and we've got bromide that can be oxidized. And so it's pretty straightforward. We don't even need to circle it, but let's circle it anyway. The oxidation is going to be the bromide to the bromine. The reduction is going to be zinc 2 plus to zinc metal. And so you can write what they observed at the various, at the two electrodes. Now, keep in mind, these are always going to be the standard colors. I should have written this on the front page. The red is always going to be the positive. The black is going to be the negative. In the video, I believe they had the red on the right. So just go with it. The anode is the positive electrode. Anode is always the oxidation. So at the oxidation, we saw a red gas. And that red gas was bromine being produced. Now, bromine is a liquid at room temperature, but this was a molten salt, and at those high temperatures, bromine is a gas. At the cathode, didn't see anything until they poured off the molten salt. And when they poured off the molten salt, we saw the gray metal. And that gray metal was pure lead. And so there's our evidence for what's going on. Let's fill in the half reactions. If we wanted to write the electrons, I didn't do this on the previous one. The electrons are coming here, and the electrons are coming here. And so we get the reduction at the cathode, oxidation at the anode. Oxidation, we have our 2 bromides, is forming Br2 plus 2 electrons. And if you wanted to write in the Oxidation number Br is 0, and that has a potential of negative 1.07 volts. And we're going to write in our zinc, 2 plus 2 electrons, forming zinc metal, and that has a negative 0.76 volt potential. And let's add everything together. We have zinc 2 plus 2 bromide. Notice that the mass automatically balances here. Electrons cancel out, and that gives us elemental zinc and elemental bromine. Now, again, this is a non-spontaneous reaction, so that tells us that in terms of thermodynamically, it's more stable to make the zinc bromide, and we have to apply the E net. Oh, I don't know why it's way over here. The E net is going to be negative 0.94 volts, and so you have to apply greater than 0.94 volts. And they just used a power supply because it was easier to do. Finally, another use for electrolysis is electroplating. Now, why would you want to electroplate something? Well, this is electroplating is how you make things like gold-plated jewelry or silver-plated jewelry. It takes a base metal, something like an iron or some other or nickel, something that's not worth as much, and it puts a nice shiny, more prettier and more expensive looking coating on it. So making gold plating is how you would, and this is how you would make some gold plating. So in this reaction, in this video, they're going to take a copper strip and a brass key are attached to a power supply and put into a solution of copper 2 sulfate. So look at the video, and then let's come back and see what's going on. All right, so as we've been doing, let's separate into the possible things in solution. The salt separates into copper 2 plus and sulfate. And it also has, we also have water present. So I've got the same kind of 4 oxidation and reduction reactions we have here, except we also see that I've put in copper 2 plus, and I put in an extra line that I left blank. The reason I put in that extra line that I left blank is that because we have in this reaction, we have both the copper strip and we have the copper 2 plus in the solution. It's all in the same solution. So I'm going to actually put the copper 2 plus in the solution now, just to show you. It's there, and we have copper. And the thing is, when we have copper and copper 2 plus, we have the potential of oxidizing that copper into copper 2 plus. So we have to put copper being oxidized, copper metal being oxidized into copper 2 plus 2 electrons. Now we have the reduction potential over here on the right. So the oxidation is going to be a negative 0.34. And my pen is leaving behind marks, 0.34 volts. There is no other possible reduction, so you can put X's in there. And so it turns out that the copper is the easiest to oxidize and to reduce. It's both. So we're going to oxidize copper at the anode, and we're going to reduce copper 2 plus. Actually, I shouldn't say copper is easiest to reduce, and copper 2 plus is easiest to reduce. All right, so on the diagram, let's label what's observed at the anode, and in the diagram, label what's observed at the anode and the cathode. That's interesting why that came up that way. Sorry about that. That looks like it's left over from a previous thing as well. So at the anode is the oxidation. So the anode is that if we were to measure it, you can't see it unless you run this a really long time. You can't see it, but the copper loses mass. And it's losing mass as it's being oxidized from copper to copper 2+. And so the copper 2+ is coming off of the electrode. Again, the copper metal isn't. The copper 2+ is coming off as it's produced. And electrons are flowing out of the anode. Electrons are flowing into the cathode. And at the cathode, we've got the copper 2+. We've got some electrons coming out here. Copper 2+ puts copper onto the cathode. And so we see the red solid that's being formed, and that is the copper metal. And like you can see, that's how you'd electroplate something. And you'd have to do something to polish it up, as she mentioned in the video. It's not as nicely polished, and they have techniques for getting these things nice and shiny and make them look pretty. The overall reaction might surprise you a little bit. So in the oxidation, we're going to take copper. Now I'm going to keep track of where that copper was. That copper was in the copper strip. And the oxidation, we're going to take that, we're going to make copper 2+, and we're going to make 2 electrons. And that has an E oxidation of negative 0.34 volts. And at the reduction, we're going to take copper 2+ plus 2 electrons, making copper. Now the copper is on the key. And the reduction potential is positive 0.34 volts. The overall reaction is that we've taken copper from the strip. Now look, the 2 electrons cancel out, but so do the 2 copper 2+. And all we're doing is transferring copper from the strip to the key. And because we're making copper from copper, we have a net voltage of 0 volts. So basically what the idea of having that copper strip in as the anode is the copper strip replenishes the copper 2+ in solution. So we always keep it at the same concentration. And theoretically, it should never run out. Now, there are going to be impurities that come out, and you're probably going to have to clean the solution. But if this was an ideal case, you would never have to replace anything in the solution. It would just continue as long as you had electrons to pump from your battery. All right, so the homework is going to follow exactly what is going on here, and do well. I will see you next time in class. Have a good day.